So clearly there were some major problems with the Edison two-wire DC generation and distribution system. In our example that we just solved, the generator voltage was required to be 438 volts to deliver 110 volts to the load because of the voltage drop across the distribution cable resistance. Edison was able to compensate this this limitation by increasing the cross-sectional area of the copper wire used to his system. And although this did reduce the effective resistance of the cables and therefore the voltage drop along their lengths, it resulted in a much more expensive system due to the increased amount of copper being used. Most of the power being radiated as waste heat due to internal resistance of these copper cables. Edison recognized these shortcomings. He was a shrewd businessman, and he proposed a practical limit of 1.6 kilometers between the DC generation source and the customer load based on the economics and technology of the late 1800s. So his solution was that there was only, a kilometer and a half between the power plant and the furthest customer away. To give you an idea, to compare that to modern times, we have hundreds of miles at least between power plants and some customers. So clearly we've made advances since then, and a lot of it is because we got rid of DC distribution. But Edison wasn't deterred about this 1.6 kilometer limitation. He did come up with a solution, and a year later, in July of 1883, Edison introduced what we call the three-wire DC distribution system, and it was introduced into operation at Sunbury, Pennsylvania. The major accomplishment of this system, the Edison three-wire DC system, was a 62.5% savings in copper as compared to the system that he had installed in New York a year earlier. The real genius of the system was that he served the load with two generators connected in series, thus cutting the current in half. And when the loads are balanced, the current on the neutral wire goes to 0 amps due to the canceling effects of the return current from the top source and the supply current from the bottom source. So you see what happens here is with this top voltage, we have a current flowing this direction, and then it returns in this direction. And from the bottom one, we have a current flowing in this direction and another return current flowing in that direction. So what that means is this middle wire, or this neutral wire, could be substantially smaller, and these other two wires could be substantially smaller as compared to the two-wire system. So he's got these two generators. They're still 110 volts. This one's 110 volt. This one's 110 volts. And so the total voltage across them is 220 volts, but if you measure just across a single generator, which is how the loads were connected with a three-wire scheme, the loads only saw 110. So substantial savings. However, the direct current had to kind of still contend with three major disadvantages. There still was a voltage drop due to internal resistance of the wire. It meant that the generators had to be located close to the load. So he was able to reduce the current reduce the current flow in these systems. So even the short distances used required very large diameter copper wires to reduce the resistance into the range of ohms per kilometer. The second limitation was that generation voltage had to be approximately equal to load voltage. Therefore, different systems were being developed to run different loads operating at different voltages. At the time, new machines were being developed. Not everything was a lamp at 110 volts. And say I invented a machine that needed 140 volts, there was no really way for me to interface it with this existing system. So different systems were coming into existence in different parts of the United States where they would all use different voltages. The third problem was that the major load on these systems was lamps, which meant they got used at night when the sun was down or during cloudy days, and at other times not so much. These low utilization voltages meant high currents, and high currents mean these high I²R losses. Most of the energy in these systems was therefore lost to heating. The major disadvantages of the DC system were kind of rectified or solved by the advent of alternating current or AC systems, primarily through the work of Nikola Tesla and George Westinghouse. Recall that in a DC system, the voltage polarity always remains constant and current always flows in the same direction. In contrast, the voltage polarity in an AC system reverses periodically over time and oscillates very rapidly. We can describe the oscillation mathematically as using either a sine or a cosine function. And here what we've got is a picture of some sort of steam-driven power plant. And we notice that the voltage coming out of that, and therefore the current flowing through the wires to a load that's connected to that, alternates with time, and it's got this nice sinusoidal shape. So the adoption of AC generation and distribution systems overcame the limitation of the DC system by using these devices called transformers to change the voltage up and down throughout the system. A step-up transformer was used to raise the generation voltage. So this side here is the step-up transformer, and it increases the generation voltage. A small conductor could then be used to transmit electricity over distances, and a step-down transformer here is used to lower the voltage at the load to levels suitable for local distribution. The Tesla and Westinghouse 2-wire single-phase 100-volt AC distribution system was placed into service in Buffalo in 1886. So they invented this AC technology. Why does this work? Well, what has to be constant across the system is power. And so I've got a voltage and a current here. I've got a voltage and a current here, and the product of the voltage and current either here or here has to be equivalent to this. So if I increase the voltage, that means the current can reduce this by the same fraction that the voltage increases. So let's investigate the implications of I²R loss by doing a very very simplified AC distribution system example. So let's look at this basically the same situation, but let's use the Tesla Westinghouse AC distribution system. So again, we're going to assume a power system, this time AC, with a voltage of 110 volts, providing power to a city with approximately 200 lamps, each having a resistance of 220 ohms. So same as before. The power plant is still located a kilometer from the city, and it's still connected with that 10-gauge solid core copper wire with a resistance per unit length of 3.28 ohms per kilometer. Now things get different. A step-down transformer at the load is used to reduce the voltage at a ratio of 1,000 to 110, which we would call the transformer ratio. And a step-up transformer is used at the generation site to increase the voltage at the ratio of 110 to 1,000. So the step-down transformer ratio is 1,000 to 110. So for every 1,000 units of voltage on the input of the transformer, we get 110 units of voltage on the output. And the step-up transformer has the opposite, 110 input to 1,000 output units. What we want to do is determine the generator voltage necessary to supply the load at the appropriate voltage and to determine the ratio of the power delivered to the load to the total delivered by the plant. So we're just investigating the same concepts. So we can create the following circuit model for the system. We present the output terminals of the generator as an ideal voltage source, but this time we use a circle containing a sinusoidal shape to indicate that the voltage is an AC quantity. So you'll notice the voltage source in this one looks different, right? It's a circle, it's got this little sinusoidal shape in it. We indicate the polarity with the plus and the minuses, and we indicate that it's a voltage. We say that it's VAC. So there's two things telling us that this is an AC voltage. It's a little repetitive, but we've got this circle, sine wave in the middle, and then this thing written VAC. So that's this thing here, that's the generator, right? Although the value of an AC quantity is actually varying continuously over time, we typically describe it using a quantity called the RMS value. We'll describe RMS in more detail in later lectures. As before, we modeled the total resistance of the distribution wire as a single resistor. So there's the total resistance of the distribution wire. Again, it's connected in series with the generator, and we model each of the lamps as a resistor connected in parallel with a generator resistor series combination. So that's this guy here again. As previously calculated, the equivalent values or the lumped values of these are 3.28 ohms and 1.1 ohms. None of that's changed from the previous example. Finally, the major change is that we have to connect the system using the step-up transformer T1. So T1 is going to take a generation voltage and step it up for distribution. And T2 we need to add, that's the step-down transformer. It's going to take the distribution voltage and decrease it for use at the load. The symbols I'm using here are for ideal transformers, meaning all of the energy input on one side of the transformer can be output on the other side, meaning this is an ideal machine. In an ideal transformer, the instantaneous power on either side must be equal because of the law of conservation of energy. So to determine the power delivered by the AC source, I need to start here at the load, and I need to kind of work my way backwards from the right to the left through the circuit. Every time I encounter a transformer, I must use the provided transformer ratio to calculate the current and voltage on both sides. So we're going to start at the load, and all I'm going to do is calculate voltage here. At the load, I'm going to say the current through the load, IL, that's just equal to the load voltage, VL, divided by the load resistance, RL. So that's 110 volts divided by 1.1 ohms. And that gives me 100 amps. And the power is therefore IL VL, that's 100 amps times 110 volts. Amps times volts is watts, so that gives us 11 kW, or 11,000 watts. So as I move from the left side of the circuit, from the right side of the circuit to the left side of the circuit, I'm going to encounter T2 here, which is the step-down transformer. The purpose of this step-down transformer is to decrease the voltage, again, from the transmission level line side to the customer line side, i.e. to step down the voltage so that the customer can use it safely. Therefore, the voltage on the left side of T2 is going to be higher than the voltage on the right side by the transformer ratio. So what I'll say is that, I'll just make some space here too. The voltage for T2, I'm going to just give it the subscript left. So the voltage for T2 on the left side is going to be equal to the voltage for transformer 2 on the right side times the transformer ratio. Sometimes this is called the turns ratio. Times the turns ratio. So in this case it's 110 volts times what was given in the problem statement was 1,000 to 110. No units for turns ratio. Notice 110 cancels out with 110, leaving us with 1,000 volts. What that is saying is if I measure the voltage right here, that is VT2L. Right? The voltage across the transformer. So by the conservation of power, if the voltage increased on the left side of the transformer, that meant the current had to decrease, and so I can say that the current flowing into the transformer, IT2 left, is equal to IT2 on the right. So current on this side has to be equal to this current divided by the turns ratio. It has to decrease, right? So that is going to be that's going to be 100 amps. And I'll just multiply it by 110 over 1,000. It's the same as dividing by 1,000 over 110. And that gives us 11 amps. So now we know the current here is 11 amps. right? Where the current here was 100 amps. So while the voltage on this side of the transformer is 110 volts, delivering 100 amps, the voltage on the far side has been reduced, or has been upped to 1,000 volts, but the current's been reduced to 11 amps. Alternatively, as power is conserved across an ideal transformer, we could have calculated the current by just saying I T2 comma left is equal to power divided by the voltage T2 comma left. So the power has to be conserved, so it's got to be 11 kilowatts divided by 1,000 volts, which again gives us 11 amps. So two different ways to calculate that. It's kind of the same logical statement. So now we know the current flowing in the transmission line section, which in it's a single section, so that loops through that transformer circuit. So now what we want to do is calculate the voltage drop across this resistor. Remember, 1,000 volts is from across those two terminals that I just indicated there, not across the transmission line. So what's the voltage drop across the transmission line? Well, in this case, VRT is just going to be the current on the primary side of the step-down transformer, I-T2 left, times the resistance RT, which in this case is 11 amps times 3.28 ohms. And that gives you 36.08 volts. All right. So the voltage plus minus here is 36.08. That's the voltage drop across the transmission line. Therefore, we can calculate the power dissipated in an RT. That's just VRT, IRT. So it's going to be 11 amps times 36.08 volts. Uh, 397 watts. So 11 kilowatts delivered to the load and 397 kilowatts delivered to the transmission line. So we're making some progress there. So now what we want to know is we know the voltage across RT, we know the voltage across T2, we need to know the voltage across the step-up transformer T1, so we're going to call that VT1 right. So how do we calculate VT1 right? Well, it's a closed loop. We can view this as a voltage source, so it's the sum of those two voltages. So it's just equal to VRT plus the voltage drop across the left side of T2. And so that was 1,000 volts plus 36.08 volts. So that's 1,036.08 volts. Right there. So 1,036.08 volts at the output side of the step-up transformer. So now that we know that, we need to move across T1, continuing to move from the right side of the circuit to the left side of the circuit. So T1 is a step-up transformer, meaning that it increased the generator voltage. Therefore, the voltage on the left side of T1 is going to be lower than on the right side by the transformers ratio. So we're going to say VT1 comma left is going to be equal to VT1 on the right side, again times the turns ratio. The turns ratio for the step-up transformer was given as 110 divided by 1,000, so it's going to be 1036.08 times 110 over 1,000. So we multiply those out and you get 113.97 volts. So that's the voltage right here. VT1, comma, left is 113.97. By the conservation of power, if the voltage decreased, the current has to simultaneously increase. So what happens was we get 11 amps. We divide it by the turns ratio, which again was 110 divided by 1,000. And that gives us 100 amps. And that is I. Gen, I guess we'll call it. So if we want to calculate the power source by the load, we can use the power formula. So the power sourced by this AC voltage source is just going to be the loop current here, IG, times the voltage VAC. Since these nodes are parallel and these nodes are connected in parallel with those nodes, we know that the voltage from the generator has to be the same as the voltage across the transformer. So we get 100 amps times 113.97 volts. And that gives us 11.397 kilowatts. Alternatively, we could have added the power from the load to the power lost in the transmission line. We would have also come up with 11.397 kilowatts, because if you remember, 11 kilowatts delivered to the load and 397 watts were dissipated in the transmission line. So different calculation, but it's the same principles, comes up with the same answer. And in this case, if we were to look at the 11 kilowatts divided by 11.397, which gives us the fraction of the power sourced by the generator that's actually delivered to do useful work in the load, we see that it's 96.25%. So previously, with the DC system that we analyzed, 25% of the power from the voltage source made it to the load to do useful work. And in the AC system, 96.52% made it to the load to do useful work.